of project members and who are doing the same topic. And we have a paper set for this session, and that's include 4 papers. And the first one, I think that's a more like more position one and more a kind of analytical one. And the rest of the 3, that's a more empirical one. So we can we have a 4 paper, and for each paper we have about 15 minutes for presentation and a very quick Q&A, maybe 3 minutes. And at the end, Professor Krajcik will have some in-depth discussion for the whole paper set. So let me have the Mihye. I think Mihye will have the first paper presentation, right? Okay, yep. let's welcome Mihye. Yeah.
Thank you.
Please.
Thank you, Chin-Chung. Thank you for joining the session on learning chemistry in immersive virtual reality IVR, a spatial analysis of students' collaborative interactions. My name is Mihye Won. As the first speaker and the lead of the project, let me briefly give you the introduction of the project and the session. Our research team has been investigating immersive virtual reality for the last several years with the help from Australian Research Council Research Fund. Our research team consists of 3 chief investigators, 2 partner investigators, and 2 doctoral students, and 1 program developer. In the last several years, we have developed 3 IVR-based chemistry learning activities. First, Winter Wonderland, Snowflake, and Hydrogen Bond. 2, a sweet taste of stereochemistry. And 3, neurotransmitter and enzyme reaction. As you can see, we placed 2 students going through the same topic in immersive virtual learning environment together. More than 130 university students participate in the empirical study, going through 1, 2, or 3 IVR activities, in addition to pre-post interviews and diagram drawing and reflection writing activities. Out of this session, we have 4 presentations. As Chin-Chung mentioned, mine is analytical framework. It is more of theoretical aspect. And second and third and fourth papers are empirical study using the framework. Okay, let's start with the first presentation. Analytical framework for students' interactions in immersive virtual reality. I will use the acronym IVR from now on. As an advanced visualization technology, IVR has captured the imagination of educators and researchers in recent years. Once put on a headset, users can see the virtual objects in 3D and interact with them intuitively as if they are real physical objects. Although IVR has shown to increase learner engagement, many systematic literature reviews reveal that the development and evaluation of educational IVR applications have a long way to go. Many of IVR applications focus on showing off cool technological features, but with limited investigation on how and why those features would help achieve learning outcomes. The evaluation of IVR-based learning activities mostly focused on usability testing with short surveys or simple information recall tests, offering a limited understanding of learner interactions within IVR and how we can use the new technology for better. As we wanted to systematically evaluate the learner interactions within IVR learning environment and better design IVR-based learning activities, these limitations were critical and real concerns for our research team. Based on our observation of students' interactions in IVR, this paper presents an analytical framework that helps interpreting the dynamic interactions between learners and IVR-based learning environment and helps understanding the unique educational affordances of IVR. When investigating the educational affordances of IVR, Norman's definition of affordances is a good place to start. He defined affordances as the interaction between the unique aspect of object and the capability of agent to determine how the object could be used. In this definition, we need to consider object, agent, desired actions, and interactions. Object is IVR's unique properties and qualities, and agent, the students, their diverse learning experiences, identity, interest, and knowledge and skills. And desired actions is, of course, science learning goals. In terms of interactions, we need to investigate how learners interact with the virtual objects and environment and other learners here. All right. But what are the unique properties or qualities of IVR that we need to observe to understand the interaction of students in IVR environment? Based on our experiences and literature, we identified two key aspects of IVR: space and movement, and virtual identity. IVR, let's start with the space movement first. IVR offers realistic sensory interactions in virtual space. After wearing an IVR headset, the physical space disappears from the view. Instead, students can see unfamiliar but realistic-looking reified objects like complex molecules. Students can grab and move the molecules as if they are physical objects. To create immersive environment, IVR hides the physical space from the view. This arrangement is necessary to make the technology work, but it gives an unfamiliar sense of existing in two spaces at the same time. The students are generally fine at negotiating between two spaces, but once they were reminded of the physical surroundings, such as a tug of a cable or hitting a wall, they become uncertain and less immersed in the virtual world. The negotiated spatial exploration had interesting consequences for learning. Before they enter the virtual space, they tend to have two-dimensional thinking of molecules, as seen in the diagram below. When they entered the IVR space, they reacted with surprise and amazement of watching the 3D molecules. As they tried to replicate their mental models with the virtual molecules, they realized that it did not work. They needed to adjust their thinking of 2D molecules to 3D molecules to complete the tasks in VR. Although they thought the virtual objects were more scientific ones and making sense, when they come out to the physical world, it was difficult for them to explain or represent what they saw and did in virtual environment. Now, let's move to the second unique aspect of IVR, virtual identity. When IVR headset hides the view of the physical space, it also hides the view of the physical body. As learners instead see themselves and partners as avatars and see their actions having consequences in virtual space, they perceive that they exist as an avatar. Learners have their own personal and social identity in physical space, but they need to assume the identity of a designed generic avatar. In our case, a floating headset and pink hands. When students realized that they could not read the facial expressions or gestures of the partner, they were annoyed at first because the communication was not just the same. But as the activities progressed, students started to realize that the masked identity gives allowance to explore the virtual space, make mistakes, and build different social relations. Some shy students became more explorative and playful to share their ideas in virtual space. Yet the masked identity was fragile. When the researchers from the physical space prompted them to do something, students slid back to their usual way of shy, passive interactions. To summarize, it appears that students need to negotiate between their physical and virtual spaces for their spatial movement and the construction of social identities in IVR as a collaborative learning environment. So how can you capture a student's fluid social construction of space and identity while learning in IVR? To better understand a student's interactions in IVR, we turn to third space theory by Homi Bhabha and Edward Soja. Homi Bhabha used the term third space as a way to avoid dualistic thinking and highlight the hybridity or multiplicity of social discourses and identities. On the other hand, Soja used the term third space as a way to bring in spatial context in human interactions, in addition to historical and social contexts. Although Bhabha and Soja did not say anything about IVR or science education, their ideas of third space was compelling. We often conceive IVR as leaving the real physical world behind and fully immersing ourselves in the virtual world. Yet, our observation shows that students constantly negotiated and moved back and forth between two spaces to interact within IVR. In addition to the consideration of spatial context, thirding as othering is a powerful lens to critically examine human interactions and their potential for transformation. To apply the idea of third space for the analysis of students' interactions in IVR, we adapted Soja's trialectic diagram as a visual model. With spirals and moving dots, the model emphasizes the dynamic interactions and transformations between learners and IVR learning environment in relation to spatial, social, historical context. The spatial is the engagement in hybrid learning environment. Social is the masked identity and social relationship with others. And historical is the learning trajectories within IVR. So the second paper focuses on spatial aspect, engagement in hybrid environment. Dewi will present the spatial aspect in relation to how the different mix or hybridity of physical and virtual world shapes a student's interactions and learning. Third paper, David will talk about the social aspects of mask identity and their relationship. It shows how the social contexts are produced and reproduced in IVR. We used two different learning setups, one with tutor scaffolding and the other without. The fourth paper talks about historical aspect learning trajectories. We will show a series of snapshots of students' interactions in IVR and how the interactions change depending on the nature of the task and time and history as students continuously negotiate their space, identity, and ideas in IVR. In all of those presentations, we will talk about what was learned and what was changed in learning and learner interactions. By adopting this framework, we are moving away from the broad questions of education affordances and learner interactions to more focused questions in relation to various contexts and changes in learners and learning, such as how are hybrid IVR spaces established and evolved in relation to learners' social and historical context? How do learners construct their identities in IVR in relation to construction of the IVR experiences? How do the construction of space and identity in IVR impact learning? How do the interactions in IVR change learners and the way we learn science? As more science education researchers investigate the educational affordances of IVR, it is necessary to establish a comprehensive analytical framework to guide the design and evaluation of students' learning and interactions within and through IVR. The analytical framework suggested here has been helpful to untangle the complexities and understand students' interactions in IVR environment. In contrast to many IVR studies, this framework places learners and their interactions at the center of analysis in relation to the unique properties of IVR. Although Baba and Soja used third space to explain complex social, historical, spatial, human interactions in larger scales, their focus on people's dynamic negotiations and construction of social identity and spatial relations helped us to adapt and apply their work to analyze learning in IVR environments. When analyzing learners' interactions using this spatial model, we were reminded that we need to practice reflexivity to avoid simplistic dualistic thinking, which Soja and Baba try so hard to guard against. Thank you so much for your attention, and I'll be happy to answer your questions.
Okay, thanks. Thanks, Mihye. Any questions? So basically, they use we use an analytical framework that's including spatial, social, and historical, and the rest of the paper. One is focused on spatial aspect, and one is on social one, and one is on historical one. Any questions? If no, we can move on the second paper. And Dewi, I think Dewi will present the second paper, right?
Yes, I will. Okay.
Okay, please. Yeah.
Okay.
Yes, please.
Okay. So my name is Dewi, and this is my first ever NARST conference. So I'm very excited to be here to present my work about students' construction of learning activities to understand the formation of snowflakes with 3 different modes. So what is the research problem here? So I'm interested in exploring the education affordances of immersive virtual reality, or IVR, and I want to compare it with other learning modes. We use 3 learning modes in this study. First one is magnetic model. It's just like your regular ball and stick model of water molecules, but this one has magnets on it, so we can emulate how 2 water molecules attract each other or repulse each other. And the second one is computer simulation. Is interactive 3D visualization that you can access with your desktop or laptop. And the third one is immersive virtual reality that Dr. Won already introduced in the previous one. So students required to wear an VR headset to transport into a molecular world, the way of the real physical world. And to tackle this learning media, I'm going to use the spatial analysis framework that already presented before, and especially in the spatial context. So interested how students explore the spatial exploration physically and mentally to develop their science knowledge. And this may be enhanced or limited by learning media affordances. So the idea is if we know how students do the spatial exploration, we know the learning media affordances. And the context, the learning context is snowflake formation. So the big question is how the snowflakes got that unique shape. So snowflakes are made of water molecules. So we start with water molecules and how those 2 water molecules interacts with hydrogen bond. And when we have more water molecule, then we get structures. Like we have tetrahedral structure here. And with more water molecule, we can get an ice like this. If you look closely, there's a hexagon pattern there. And that is the reason why snowflakes has 6-fold symmetry. So students explore their idea using first magnetic models. So we have pre and post interview between session, and then continue with computer simulation. And then lastly, the immersive virtual reality. So the whole session, learning session, is about 2.5 hours to 3 hours. We have qualitative, we have data that we analyze qualitatively. So the data is the video recording of learning session, pre and post. We also have students' diagrams of 7 pairs of first year chemistry students, so total of 14 students. And we coded first of their spatial exploration, so how they move in physical, virtual, and hybrid space, and their social exploration, so exploratory talks, whether they're questioning or elaborating their ideas or they not, or they just simply, yeah, I agree, and their social dynamics with each other. And the third one is their conceptual exploration. So what do they learn after all this learning media? So let's dive into the results. So I'm going to one by one, learning media, and have this spatial social conceptual exploration. So the first one, magnetic model. What is happening here? We have 2 students holding their own magnetic model there, and students and the molecules were in the same physical space. And there can feel the magnetic force between the model to understand, oh, oxygen, or hydrogen repulse, and oxygen, hydrogen attracts. So with that tenet of how water molecules interact, they can create several structures. We have tetrahedral structures, and they can create another structure, ring structure here, the hexagons. And then they can try out different kind of structures like this one and realize, and shake it and realize, oh, it's not stable enough. So these 2 structures must be stable and must have kind of link with the snowflakes. So with that spatial exploration going on, how the social exploration looks like. So again, we have 2 students with their own model there. So initially students say a few words explaining what they saw and then play alone with their own model. So the interviewer will step in and say, do you notice anything? This works to like dig in what the students are thinking. However, the implication is there's a one-on-one interviewer interaction, so not student-student interaction. And then students may feel the obligation to provide an answer, a correct answer, not just anything that they think of. So it's kind of like restricted. So the exploratory talk, meaning the questioning and elaborating, is between the interviewer, purple, and one student in green. The other student will kind of like support or just like agreeing what the other students are talking. And what do they learn? Mathematical model. So obviously the traction and repulsion because of the magnetic forces, and they can explain the simple structure of tetrahedral and hexagon structure. So what is the link with the snowflakes? How does it look like? So 4 pairs actually have an understanding, oh, a hexagon in isolators must be responsible for the 6-fold symmetry of snowflakes. However, in this mode, because this is what they see, and they literally take it, this is snowflakes, so they don't have the sense of scale yet here. So because obviously the real snowflakes are made of billions, many times molecules than just a monolayer of these molecules. So the second one is computer simulation. Same like magnetic models, we still have 2 students there, but then the molecules are in the different space, in the virtual space. Then the bridge between the students and the molecules are 1 keyboard, 1 mouse, and 1 screen. So we have text, instruction, graphs, and 3D model there. But so the students have to spatially explore what is happening there in the virtual space. So, and the sense of depth is lacking for 4 of 7 pairs we have. So I'm quoting what Kim said here. I think it's hard to like tell the depth. So if you can see the molecule here, you cannot really tell whether it's in front or at the back of this molecule. So sense of depth is lacking there. So what is the social exploration here? We have 1 person in control while the other is navigating, and they switch control after each task. So the pilot usually describe the result of their actions, simply like a short statement here. Oh yeah, there's electron rich and that's electron poor. And we have the co-pilot who navigates. Here in yellow have all sorts like suggestions. So the implication here, the co-pilot is like a driver in passenger seat. So it's kind of dominating the pace of exploration here. Then students did not deviate from the text instruction. So the text instruction kind of hindered them for exploring more of their idea. Then the interviewer is still there, even though the interviewer did not say anything, but the presence itself might prompt them to not fully express themselves, their opinion. So the exploratory talk is, you can see in green, is the co-pilot who dominating the pace, and yellow is the pilot kind of like supporting the co-pilot. So what do they learn? So this is the numbers of magnetic model. You can see there's a lot of monolayer going on. But what happened here in computer simulation? So students can explain attraction, tetrahedral, optimum orientation. But if you notice, the topic about structure is not really mentioned because maybe the sense of depth that's lacking. So you cannot see the back and forth on the 3D. Even though it's 3D, but you see it from 2D monitor. So it's kind of lacking for these students. And the linking ideas. So it's less than magnetic model. So to quote what the students say, computer simulation is help to understand how water molecules interact, but it didn't really help me to understand snowflakes. So the big picture is not really come true through this computer simulation. So we have then the third one, the immersive VR, virtual reality. So what's happening is we have two students sharing a synchronized physical and virtual space, creating a hybrid space. So each student has a full control of the molecules and could interact with the molecules. So it prompts them to do more of active learning. And it's not like computer simulation with one who has control. Now both of them has control, and not like magnetic model when you have holding your model to yourself. This one shared. So, and they have to apply what they learned before in the context of 3D space. And the spatial information is embedded in the space. So there's a direct link. So for here, for example, student put up the isolated there, up there, and then take the snowflakes and put it there. See the parallel of hexagon in isolated and hexagon in snowflakes. It's like total aha moment for all student pairs. So what is social exploration looks like? So students are immersed, and even though the interviewer is there, they don't care. They saw, for example, here they saw the snowflakes falling from the sky and thought about, hey, how about the snowflakes from mountains of China and snowflakes mountain of Switzerland? So you can see they're more free to voice their opinion, even though it's not really directly related to the chemistry learning. So they're more free. And then here we have two students in different positions and see the same latest, but from different angle. Students recognize this. Students realize they occupy different space and literally have a different perspective. So they talk about, hey, how about when you look it from there? So they kind of, what do you see? I see this. Do you see it? So the implication is more exploratory talk to reach a joint understanding. So we can see there is shift to a more equal exploratory discussion compared to other learning modes. And what's the learning? What do they learn? This is the number of magnetic model briefly. This is the computer simulation. And now it's the VR. So all understand about structure and not about the traction, not mentioning about traction, maybe because there's not enough haptic feedback, unlike in magnetic model where you can feel the forces. So they explained it well as well. And linking ideas, no more misunderstanding about monolayer. So everyone explain it in relation to the 3D, and even more students move beyond the parallel of hexagon in isolates and hexagon in snowflakes, and think about scale. Like, oh, there's so many water molecules in there, so they must be responsible of the randomness. Then that's why snowflakes has different unique branches, not only explaining the 6-fold symmetry of snowflakes. So yeah, so and happy ending for students there. So what do we learn? We contribute from the study. We demonstrate that every learning media has their unique affordances, and students tap into that and construct a different spatial, conceptual, and social experience there, which result in different learning outcome. And using that spatial analysis framework, we open up and allow us to investigate more of educational possibility and limitation of each learning materials there. So yeah, we have to treat space here. And thank you for your kind attention. Welcome any feedback to improve the study. Thank you.
Okay, thanks. So basically, you try to compare, or we try to compare the 3 modes, yeah, and the one is more physical one, and the one is about computer simulation, and the final one is about immersive VR, and you try to understand their learning during the process. Yes. Yeah. Okay. So any questions? Okay. If no question, you can ask the question. You can have a question by the end of this session. So we can go to the third paper. That will be presented by Devi. And that's about the social part for the paper. And Devi, you can start right now. Thank you.
Okay, thank you. And Mihye, thanks for arranging all this and getting everything put together. So this is the third paper looking at comparative analysis on the impact of scaffolding on students' interaction with IVR. So here's the theoretical structure that Mihye talked about, and the question we're asking here is, how do students construct their learning experiences in IVR with or without a researcher providing scaffolding? So this is the physical environment that took place in a lab at Curtin University. So we have students in an environment of where they can participate in IVR. They have headsets and have space to move around. In this study, we have 14 pairs of first-year chemistry students. They're dealing with the same topic, IVR program on water molecules and ice crystal formation. Group A has an instructor, chemistry instructor, that is guiding the students with asking questions. And Group B, there is an observer there, but not providing any questions or comments. So what are they learning? They're learning the simple structure that relates to 2 water molecules creating a strong hydrogen bond and connecting the water molecules to a central water molecule to create a tetrahedron shape. This is what Dewey was referring to. In a more complex structure, we're moving to looking at connecting 3 layers of water molecules to develop an ice lattice, and the ice lattice has the same as the shape of the snowflakes. So the students can move the material around to determine this actual shape. So now I'm going to look at the results. We're dealing with spatial explorations. social interactions, this exploratory talk, and conceptual learning that was identified by Dewey. So here's a situation. We have 2 students and an observer. This is group A. And we're mapping the students' social explorations with every time they move, they get placed somewhere here, 2 different students. And as they move around, you can see where they've been. And the darker color means that the students stayed in that particular spot for a longer time. And this was the situation creating hydrogen bonds. This is the information from the IVR program. If we look at all 7 groups, you can see what happens where the with group A, with the tutor, the students tend to stay mainly in their own place. They realize where the tutor is, and I guess they stay away from the tutor. Again, the dark color means a longer time was spent in that position. Same activity with group B, and you can see there's more movement of the students, that they are not inhibited, if you like, by needing to be aware of where the observer is, because they're not asking any questions. So students moved around, and as you see in some cases, they really moved around, like this particular one. The students were intervening with each other with the headsets on, remember. With the ice lattice, with group A, there's more movement with the students in this case. They moved around more to look at the complex structure of the ice lattice. Again, the darker color is telling you that the students are staying in the same place. In some cases, like this one here, the students really move around a great deal. If we look at group B, which is the students without the tutor being there and the ice lattice, we see that the spatial exploration is very similar to group A. Students swapped places and covered more area. So in this particular case, unlike the first case with a more simple exploration, the students moved around in group A and group B in a very similar manner. So we're trying to explain this. So what about social interactions? With group A, we have a tutor and 2 students, and you can see the kind of things that they're looking at. And if you examine the dialogue, it's like one student reacting, answering the question. So tutor saying, let's say you have 1 water molecule, where would it bond? And student saying one water molecule, well, just sit, it would just sort of keep building. And so there's a dialogue. And so you have tons of water molecules. Where would they go? They would attract each other. So it's just a dialogue almost that you might find in a classroom, not in an IVR studio. Group B, social interactions. The students question each other. There's no other person there other than the 2 of them. And the students perform the action. So you can see what's happening here. How do you make a hydrogen bond? And Elena says, did you do it? And how did you make it? And they're looking to find this green nature of the interaction, because the green is representing the bond between the hydrogen atoms. So seeking a joint agreement with partners instead of focusing on the correct answer, as the student did when they were responding to the tutor. And if we look at this diagram, I need to use my cursor to just point out that the blue here is the instructor dialogue, and you can see it's less with the complex structure. The green is one student, and the dark color is the exploratory talk, and the other color, orange, is the other student with the exploratory talk, and you can see how this differs. In the simple structure, the exploratory discussion in group A is between one student and the instructor. And you can see this with all these different colors. For group B, the students are more equally presenting their discussion. Not exactly equal, but they're more equal than in this situation here. And then when in the complex structure, which has followed the earlier structure, the instructor talks less, and the discussion tends to be dominated by one student for both groups A and B. So this is the blue student is having more to say, more interaction, more questioning than student who is in the orange color. So the social dynamics changes with the nature of the task, and this is part of our investigation. Looking at the same conceptual understanding that we're looking for, that Dewi presented in her work, you can see something very distinct here, that in terms of group A and group B, in terms of mentioning the concepts, so they're working with these concepts, it's pretty similar what the two groups are doing. However, when it comes to explanation, the group B that do not have the tutor providing questions or guiding is much more evident when the students are working together. In terms of linking ideas to form the more complex structure, and remember, this is now where the students in both group A and group B were moving around in a very similar manner, unlike the more simple concept. You see it's very, very similar. So if you look at some of the discussion with group A, the instructor is saying, what does the number mean to you? And Lisa is saying bond angles. And instructor says the A on top is the distance. Okay, if you look at the color of the bond, that orange, and it was green, then it's green. Oh, there we go. So that they work out that green means it's correct. So they like finding an answer to the question. And they're looking at features and ideas in terms of numbers and colors. With group B, they're interacting at a more intellectual level. Yes, it's a really good green, so that's actually bonding occurring, or the intermolecular force. So then we add a whole ton more, and we've got the snowflake. And then another little bit of dialogue. when they don't fit the molecules together, and they realize that there's no bond, or the bond is so weak. So in the first group A, we got mentioning features, ideas, but in the second group, without the tutor, we got explaining ideas, looking at optimum orientation and bond strength, and link to explain the formation of a snowflake. So what does this all mean in terms of our contribution? And if you remember, this is the point that Mihye brought out as a key question in her presentation. Students in Group A did not get the full benefit of the immersive VR because they have to navigate two separate spaces. They have to separate the real space that they're walking around in. And remember, in the earlier study, the student tend to stay in one position, and they have to consider the VR environment as well. So we got the physical environment, which is avoiding physical obstacle in the room. The initial more simple activity, the students tend to stay in one place. They didn't in the more complex snowflake structure. And intellectually, with Group A, they were trying to give the correct answer to the researcher, whereas with the Group B, they were engaged intellectually with the tasks themselves. So the instructor's technique to interact with students in a physical space may not work the same way when applied to learning in IVR space. In fact, it would appear to be restrictive of student learning, particularly in the more simple activity. So rather than simply having the instructor during the IVR session, the role of the instructor to support students learning in IVR needs to be further examined. And this is an aspect that we're looking at in some detail. So that's the end of the session. I'd like to thank you very much for your attention.
And I found that we have an online chat room, and some people, some participants, they also post some questions there. Yeah. So
right.
Yeah. Do we got some questions there?
Yes.
Okay.
Yeah.
What do you think a possible solution for the tutor role here? Yeah, because you have the first group, the Group A, with the scaffolding by the instructor, and the other ones that's without instructor. And maybe, what do you think? Yeah, if the instructor want to play a role in that kind of setting, what do they need to do? Yeah.
Are you asking me, or shall we answer this question here?
Because if we have time,
So the question is for me, what do you think is possible solution for the tutor role here? Could tutor training be helpful? Example, less directive questioning, or do you feel it's just better not to have a tutor during these explorations?
That's also my question. Because
right.
if we want the instructor to help, how can they do?
I think less directive questioning is the obvious one. And I'd like to bring Mihye in here and ask her what she feels about this.
Okay, the tutor here in this setting is very experienced chemistry tutor. He is not really directive in terms of his teaching style. He was asking probing questions, bringing in students' ideas, and he was quite skillful in that. But because the position of him outside the virtual environment, solidly in physical environment, and students cannot see him and cannot interact with him naturally, it really prevented him to interact in a more exploratory way. And I don't think it is fair to blame his skill, because he is quite skillful. But our premise is that because the separation of tutor in physical space while students are in IVR space, the separation really prevented them to engage in more collaborative, exploratory discussion. And the student's conception of tutor's role really prevented him to interact with him in more collaborative manner. So I think it is interesting. It is an interesting question to investigate further in terms of how different type of probing questions change the dynamics in students' interactions. But a good question, but we think it is better not to have the tutor in this setting for now. But we may change our conclusion later on. Thank you for the question.
Yeah.
Thank you, Mihye.
Okay. Yeah.
We also
Or
have
maybe
another question.
Yes, please.
The question's in the chat from our virtual attendees. And Zainab has asked, who were your collaborators that designed these virtual reality environments? And what was the prototyping process like before you shared these with your students?
Yeah, I think Mihye, yeah, please. Yeah.
I saw the question late, so I was going to answer the question after all the talk was done. But let me answer the question here. As I said in my presentation, it took several years to develop the program and test the program and reach the place where we are now. Initially, we had a collaborator who has specialty in chemistry instruction, chemistry education, and chemistry visualization. The two investigators, they are not here today, but they have quite extensive experience in chemistry instruction and visualization, and they contributed to the storyboarding and development of the program of IVR. And we had the visualization specialist in the university, and they could recruit the computer science students and volunteers to help develop the program. And initially, when we developed the program, we were really ambitious, assuming students would have really good chemistry understanding and they will showcase their understanding in IVR environment. But we realized it was too ambitious, so we had to provide more feedback on students' progress, and we redesigned the program for many times. And now the program is developed by the designated program developer, but we are attracting more volunteers who are willing to support the program development in IVR. And I am thinking you are asking the question in terms of what could entail for you to develop IVR applications. To be honest, it is quite complicated. I was tempted to just give up on the idea of developing our own IVR applications and use someone else's program and just test it, because the process itself was quite hectic and tricky. But outside programs, they do not allow multiple people interacting to learn science or any science topics. So we had to develop a program that fit our pedagogical ideal of IVR interactions. So that's why we went through the multiple iterations of development of IVR applications. Does it answer your question?
Yes, and you answered it well, because it was very complicated.
In one way, it is very complicated, but on the other hand, it may not be as complicated if you had the understanding of what it could entail in the beginning. But because we didn't have the understanding in the beginning, it was more complicated than necessary. So if you want to develop a program and get some feedback on the process, you are welcome to send me email and seek our team's advice.
Yeah, thanks. Yeah, I think that's a very common questions when we experience some innovative technology, we will ask, yeah, how can do that, and who can help? And one quick questions, because Davis and Dewey's paper, they use the framework mentioning ideas, explaining ideas, and linking ideas, and how these labels come from. How did these three labels come from?
Okay, let me try to answer the question. So thank you for the questions. Initially, trying to find out what the students learn. So we have a list of learning goals, and we go from there. So what the students learn in each mode. Yes, tick the box, like hydrogen bond, yes. But then we wanted to know more than just ticking the box of they reach this kind of learning goal. We want to see whether they can move further. So I took inspiration from the classic Bloom taxonomy of having their description towards more of explaining and applying, and then simplify it a bit. So we only just have these three levels of mentioning, explaining. So students, we have a tool of learning media. So the basic interaction explanation that I saw from students' interaction is direct mentioning. So this is a model. Oh, I can see this. The shape is band shapes. So it's just mentioning. But then students some students would elaborate from that to explain why is it band shape, why is it hexagon shape. So that's why the second level. And since this is about snowflakes, so I'm trying to see whether students could link those ideas. So yeah, just try to have a comprehensive level. So that's what I get.
Yeah, I think we create that label by our own, but that's a label, from the very fundamental to more higher level conceptual understanding, because you can have some integration for other among different concepts. That's linking ideas, something like that. Yeah. Okay.
Yeah.
Okay. So because I need to control the time. Yeah. So can we go to the last paper presented by Henry? Yeah. Thank you.
Yeah, I have shared my screen. Okay.
Yes, please.
Thank you everyone for joining our session. My name is Henry Matovu. I'm a PhD candidate at Katni University. This presentation is about progression of students' interactions over 3 immersive virtual reality learning activities. We have reviewed literature about students learning in IVR. Many science educators are going for this technology to improve the way students learn science. However, evaluation is normally for only one-time learning opportunities that the educators provide to students. Therefore, there is a need to investigate how students' prior interactions in IVR may shape their future interactions, and that can help us understand their learning benefits. So this paper digs into the historical context of students' interactions in IVR. And the question we're asking here is, how do university chemistry students' spatial and social interactions in IVR for chemistry learning change as the students get accustomed to the learning environment? So to answer this question, we designed 3 learning programs. The first one was about intermolecular forces in snowflakes. This is what David and Dewi have gone through. So students played around with 2 water molecules, explored the nature of hydrogen bond, and built more complex structures to explain the shape of snowflakes. In the second activity, students explored polarity and stereochemistry in the context of tests. So students constructed 2 stereoisomers of phenylalanine and their electron density maps and tried to identify which of the stereoisomers would activate a sweet test receptor. The third activity was an enzyme substrate reaction. So students could zoom in and zoom out of a protein structure, could explore different model representations of a protein structure. They could walk into the protein to explore how the shape and electron density would influence the reaction. Participants in this study were 35 pairs of first and second year university chemistry students. Each of the activities was followed we started with a pre-interview, then the VR session, and then a post-interview. We collected data in the form of videos, audios, screen capture, as I'm going to share, and some student-generated diagrams. Analysis is being done qualitatively, and we are digging into how students navigate the space, how they interact with one another, and what kind of concepts they learn, and what is the quality of their conceptual discussion like as they go through the learning activities. For this particular presentation, I'm going to share interactions for two students, Sandra and Dom, to show how students' interactions changed over time. And I'm going to focus on the first and third IVR activities. These results are preliminary and may not be generalizable to all the student pairs, but they will give us an understanding of what is happening in some of the student pairs. The results, in the first IVR activity, the Snowflakes one, we realized that students' interactions change based on the nature of the learning task. So from simple tasks to more complex tasks. But we also observed that the level of students' conceptual discussion was largely at superficial level and did not change in this activity, did not change much. For example, this is a simple task where students were exploring hydrogen bonding between two water molecules, and then later a simple task creating a simple tetrahedral unit. Initially, students stood each on a different side of the IVR space. They did not walk around much, and they hardly swapped positions. This is possibly because they were just getting used to the IVR interface, and they were still aware of the physical space. So they fear to walk much because they think they will run into barriers in the physical room. The students also stood opposite one another, looking at each other's headset as if they were trying to read their facial expressions like they would do in a face-to-face situation. Socially, we also observed that instead of working collaboratively on the tasks, we observed that students divided the work and they tended not to talk much to each other. So these two tasks were characterized by some moments of silence and individual activity. Here we think it's because the students were not yet sure of what to do in these tasks because they were the first tasks. And each student tended to first explore the ideas on their own before they could share with the peers. In terms of their conceptual exploration, we observed that students tended to apply directly their 2D understanding of molecular interactions to the 3D molecules in IVR. This is a pre-interview diagram that the students had in the beginning before IVR. The students had an idea of electron-rich, electron-poor regions in water molecules, but they were not sure of how to orient these molecules. They did not have an idea of directionality of a hydrogen bond. When they went into the IVR space, they did the same thing. They applied 2D reasoning. They tried overlapping red and blue areas without any sort of directionality, or simply stacking water molecules. And this made them struggle to create a hydrogen bond. In terms of their conceptual discussion, for most of the time, the students were discussing concepts at very superficial level, just identifying features. In this transcript, the students are talking about the effect of the angle orientation between water molecules and the strength of a bond. So here they are talking about, see how, does it change color, or see how it's red there? And then Dom, it was getting stronger as we were doing that. And then it turned. But the angle was, see, it's red, that's probably not good. Then it's there's like a green zone, I guess something like that, where, yeah. So the students' discussion is just talking about what they are saying, but they are not really digging deep into why it is happening. In various cases, students try to link the chemistry concepts to the visual cues. For example, here, the students are discussing the effect of distance between water molecules on the strength of a hydrogen bond. I think the thickness is representing a strong bond. I think there is an ideal distance. If you get too close, then you get the repulsion. So there was a bit of linking the chemistry concepts to the visual cues, but these were very rare cases. That was in the simple task. When the task became a bit more complex, here the students were supposed to connect clusters of water molecules through hydrogen bonds to form a single layer of ice. The students built on their experience from the first two activities or first two learning tasks to connect hydrogen atoms to lone pairs and form green bonds, strong bonds. We also observed that the extent of student navigation increased in this task, possibly because the students were getting immersed in the task, and then they were also starting to appreciate the 3D nature of the IVR environment. We see students changing positions more frequently. We also noted that prior IVR experience did not influence the students' interactions much in this activity. Sandra did not have any IVR experience, but was the one who was identifying the relevant patterns in water molecules to help them connect the clusters, and was the one who was guiding the peer. The peer Dom had extensive IVR experience for gaming, but was dependent on someone who did not have IVR experience. Socially, the students noted from experience that in the individual approach would not help them complete the task here. So they adopted a driver and passenger seat strategy. So where one peer was identifying the patterns and guiding the other one who was manipulating the molecules. In the transcript, we see Sandra saying, so you need like the opposite. You need a lone pair here and you need a hydrogen there. And then we see her again saying, yeah, I think turn it upside down. Maybe, yeah, turn it this way. So it was more of Dom manipulating the molecules and Sandra guiding. In more complex tasks, where here the students were connecting 3 layers of water molecules to create a lattice and use that lattice to explain the shape of snowflakes, we see students walking more and working collaboratively. So here we see, hold that one there, and I'll get the top one, right? Dom, is it supposed to be like this? Sandra, how do we align them? So the students are questioning each other. They are discussing strategies to complete the task collaboratively. However, we noted that their conceptual talk did not go beyond the superficial level. Again, the students were identifying features and not going deeper to explain why. After creating the lattice structure and observing hexagonal patterns, they are saying, this whole time we've been talking about molecules being in hexagonal shape. And if you look at the snowflakes, they've got 6. Yeah, they're all like 6. 6 structures kind of thing. 6 ways it can be symmetrical, right? Yeah, I see what you mean, because it's hexagonal. So they identify the hexagons, but they don't go beyond that. And this was the first IVR activity. When they went to the third IVR activity, after going through the second and now the third, we observed that the students' social and spatial interactions changed. Students did not hesitate to move around anymore. They explored the IVR space extensively. This is because they had probably got used to the interface. They don't fear to explore. They're building on their prior experience. And then the tasks in the third IVR activity required the students to explore the protein structure, move to different points to explore electron density and structure. We also noted that instead of standing opposite one another to look at each other's headsets, students must have noted that they could not read each other's facial expressions. So they decided instead to stand beside each other to look at the same thing. For example, here we see students constructing acetylcholine, which was the substrate molecule. The students are standing beside each other to face in the same direction instead of standing opposite to look at each other's headset. The students' approach to the task was also more collaborative. They freely shared ideas and discussed strategies to complete the tasks. We also noted that unlike in the first IVR activity, where a change in task complexity was changing the interaction, the students' interaction in the third IVR activity did not change much depending on the nature of the task. This is a complex task, more complex than simply constructing the substrate molecule. So students are supposed to orient acetylcholine at the entrance of the protein in a way that would allow the reaction to take place, the reaction between the enzyme and the substrate. Again, we see students standing beside each other, and then students taking collective responsibility in solving the tasks. The transcript here shows students questioning themselves, is that angle okay? How do I get this? Maybe you should not do that. Maybe you should put it at the entrance. So the students are discussing their strategies. They are not working individually, but collectively as a team. Their conceptual exploration also changed. Students consistently integrated prior knowledge and experience in their discussion, and reasoning was visible in their conceptual discussion. This is the same task orienting a scaffolding at the enzyme entrance, and they're trying to justify what they are doing, Sandra. And then the oxygen is electron rich, and we've got a blue region just at the bottom there. Yeah, I think you're right, because the nitrogen part is going to be oriented towards this area. Yeah. And then the ester section is going to be oriented towards the blue part because that's the electron rich, electron poor. So I think, yeah. So the students were building on their experience rather than simply mention ideas. They try to link how these ideas, how the features of the IVR environment would impact the reaction. And you see reasoning, collaborative reasoning visible in the students' conceptual discussion. So this is a summary of the students' interactions. So like I said, in the simple tasks of IVR activity 1, the students were hesitating to move around. They were more individualistic. They applied 2D reasoning to a 3D environment. And as they went to more complex tasks, they started building on their experience, moving around more, but again, with opposite perspectives. They changed strategies dynamically from division of work to assuming roles to collaborative action. And the students' conceptual discussion is largely superficial. That is the first IVR activity. But when they go to the third activity, they use their experience, they build on that to walk around more to explore the different features. They assume fairly similar perspectives because they cannot read each other's facial expressions. They take a more collaborative approach, and the conceptual discussion is more elaborate. So what do we take from this? We noticed that despite being aware of the effect of novelty of learning environments, most educators still investigate learning benefits for single IVR sessions. So we try to overcome this. We use 3 collaborative learning activities to explore how students' prior IVR experience would influence their spatial and social interactions and their learning chemistry in IVR. We observed, as I have gone through the data, students' spatial interactions, social interactions, and learning change dynamically throughout the learning tasks. Therefore, investigating the historical context of students' learning in IVR can help us to better understand their spatial and social interactions while learning in IVR. Thank you for your attention. I welcome any questions.
Okay, thanks for Henry's presentation. And he tried to compare the interaction across different tasks. And when they experience different tasks, how they change their interaction. So, any questions?
There is a question I
There's
typed
one.
in. Yeah, and one more coming.
Yeah, I wonder what kind of protocol was used to evaluate the students' conceptual understanding. Is any specific source of protocol that they can share with us? How
Sorry?
can you see the chat room?
Yes, I can, but okay, how do you rate the student's standing position and so on?
Sorry, my mistake. I copied the question to Chin-Chung only. So I copied the 2 questions.
Sorry.
Yes, the second one is the first one. So if you can answer the question, Henry, it'd be great.
Yeah, so the first question is, how do you rate student standing position and social interactions? What kind of social interactions do I expect from students when engaging in IVR? Again, because the students cannot see the faces of each other, without that understanding, when they first come into IVR, they were trying to read each other's facial expressions. It was interesting because that is what we would do in normal, in face-to-face interactions. But so the students are, even though they have been thrown into this unfamiliar environment, they're still trying to apply based on their everyday experience. So, but with time, they learn to navigate the new world. So they build on their experience. That is why we see the change from looking at each other's headset and then going to more of looking at the same thing. Probably they do that. They try to look at the same thing. We also saw cases where students were questioning each other. Do you see what I'm saying? Can you see it? Can you do this? So the interaction in IVR was a bit different from what we expect from a physical world. I'm not sure if I'm answering your question correctly, but their prior experience was initially shaping their interaction in IVR, but with time, they learn to navigate this new world and they try to change accordingly. What kind of protocol is used to evaluate students' conceptual understanding? Again, because we had specific learning goals, specific learning objectives, we had the concepts listed, what we expected students to talk about, and then we looked at the level at which they talked about them, just like in Dewi's analysis. So whether it is simply mentioning, that is the superficial level, or explaining, or linking, or integrating prior knowledge, that is what we did, kind of Bloom's taxonomy. Yeah, thank you.
Yeah, okay, thanks. And I think we still have 10 minutes left. So can we have Professor Krajcik as a discussant to comment on this paper set, please?
Hi, can you see me?
Yeah,
okay.
Yes.
So it's a little, I'm looking out at our audience. Actually, I'm looking out at 4 bright lights. Anyways, I want to thank you for inviting me to this session because it really was interesting. In some respects, if you stop and think about this session, we're looking at what the future of education might be like. Now, these immersive IVR, immersive virtual reality sets are really expensive, but you can imagine in 10, 20 years, 30 years, if cost of equipment goes down, how this could really change how we learn, particularly chemistry, but other fields as well. So I was really pleased to be part of this because it's sort of the future where education is. And I'm going to try to highlight within the short time I have a couple of points that I think are really important. So the first thing that I really found valuable about this session is where they try to introduce a structure to think about IVR. And that is, their notion here is that when you're in an immersive virtual reality setting, 2 things are going on. You're both in a different physical environment where learners can actually experience in real time being in the micro world in this particular case. That's one aspect. But the second aspect is they're taking on their personal identity. So this notion of talking about a new framework, this framework of this hybrid space, because there's both a spatial, there's a physical, there's both a spatial, a social, and historical aspect, I think is really important. And so that a learner actually takes on a new identity within these kind of spaces. I think that's the point they're trying to stress. And so I found that a very interesting framework to think about it. Now, given that, I'm going to raise a question for the group because I think it's really important. I was actually quite fascinated about how, and I'll bring up a couple points about this. When the instructor was there, you saw less conversation. So I was curious, what would happen if the instructor was part of the immersive virtual reality situation and not just outside of it? Because in this case, what you had is you had a case where the instructor was outside asking questions, or he wasn't there at all. So what would happen if the instructor was part of the virtual space? I think it was Gavin who asked the question, what about if, so this is sort of related to this. Gavin asked the question, Gavin Farmer was on the chat. The question he asked was to David, what happens if we would give the instructors some training? Now, one of the things I noticed was that a lot of the questions that the instructor was actually asking were kind of very directed, right? He wanted a right answer. I didn't see once pointing to the other person and say, well, what do you think, right? What are your ideas on these situations? Really trying to get dialogue between the two individuals. And perhaps that resulted because that individual, that instructor, wasn't part of the immersive environment. So if he becomes part of the immersive environment, what happens then? So I'd really like to hear the group's comment on that. I also found that this is now going to the second paper. I really like the 3 tasks, right? So, my background is in chemistry. And I don't know how many of you guys are chemists. I'm actually more of an organic chemist than anything. And I remember playing for hours with these molecular kit, these little tiny kits where you'd build molecules. And so what we saw in this case were kids actually experimenting with these magnetic molecules to kind of get a sense of feeling the force about why these things would snap together in certain positions and not. And then you go to a simulation that kind of, simulations are cool because you get to visualize the molecular world, particularly when we're talking about the three-dimensional structure of ice, right? Which is really hard to imagine if you just to create that image in your head. So to be able to see that simulation is pretty cool. But then you get the immersive virtual reality, and you actually, in some respect, put all 3 of them together. And actually, it's even more than putting all 3 of them together because you're really in there. So if you're in a real immersive virtual environment situation, you actually can feel stuff, you can see stuff, you can interact with it. I would imagine the learning would be so much more powerful in that particular case. Now, the same thing is true with the third paper, right? I really liked his comment that a lot of the previous studies, when you're talking about immersive virtual reality, are typically done in one situation, right? And we look at what happens. And if you think about education, that is typically what we always do. We do one-shot studies, and we don't really try to study what actually happens over time. And in this particular case, we get to look at what actually happens with learners and how they're being able to use this virtual environment over time. And one of the things we see is they become more comfortable moving around. They become better at dialoguing with each other. And I think this really brings in that sense of hybrid space. Those students who can actually interact in these environments over time actually do take on this new identity of being in this virtual environment and be able to interact with these things. So it's not always simple to jump into a new situation like we always try to do in education and just test it, just examine one situation. So I really appreciated this particular example where we got to look at students actually in this very rich environment over 3 different situations, getting from more complex, simple to more complex environments, right? I would just love, David, you have to invite me to Australia so I can go inside this virtual environment and play with these enzymes. I think it would just be a wonderful experience.
Right.
Anyways, thank you very much for inviting me. There's only 3 minutes left. I actually want the team to be able to respond, and I also was given the task to see if there were some other questions in here to make sure that the presenters would answer them. Pong He actually asked a pretty interesting question that I don't think was answered. I guess I would like to hear a little bit more about this. And it has to do with how do you define the levels? So the levels were mentioning, explaining, and linking. And he says, I wonder how you identified these 3 levels. I don't think you guys answered that. So anyways, I'm going to stop there. Thank you very much for some really fascinating work. Thank you for inviting me. Thank you for introducing this group to this fascinating vision of what education might look like in the future. So thank you.
Yeah, thanks,
Thank
Joe's
you, Joe.
comments. Yeah, and do anyone want to respond to Joe's questions, especially for how about the teachers can immerse into the VR, and how about if any training can help, the teachers to play a better role in that kind of IVR environment. Yeah,
Yeah,
anyone want to-
particularly if they're in the environment, right? I think
Yes,
I think that's what I would love to see is putting the instructor in the environment who is actually, I'm getting a nod from one of the participants in the audience too, who would like to hear your response, right? It seems like it would be so valuable just to put them in there.
Okay, thank you for your question and comments, Joe. And just to start, you are welcome to come to Perth and experience IVR headset. Initially, we were planning to bring all the IVR headsets and the equipment to NARST and give the opportunity for all NARST attendees, but we are stuck here in WA, in Australia, because our university is not really allowing us to fly to attend conference. But thank you. Okay, the tutor's role in IVR. It's unfortunate that we couldn't really capture the tutor's probing questions there in the transcripts. But as I said earlier, the tutor is quite experienced in probing, and initially he would say, "What do you see in there? Do you see green bond?" And he would ask the question of, "What does it represent, and what do you think? Why don't you discuss with your partner?" He would ask that kind of question, but it always came back with answering the tutor's prompt instead of the students interacting with each other. And the tutor in the physical space can see what students are seeing because we had two monitors streaming what they are seeing in virtual environment. And the students cannot see the tutor, but they could feel where he stood because they could hear the voice of the tutor. So it is a bit tricky situation. We never tried putting the tutor inside the VR space because the program was designed to have 2 students only instead of 3 people. So it was tricky to put 2 people inside the VR space, and we didn't really attempt to put 3 people in the space because it would complicate the setting a bit more. So we wanted to go step by step. So we had 2 students in VR. So I think it's really good idea to put tutor inside and see how it changes the group dynamics. And Joe, you mentioned that how we came up with the 3 levels of conceptual understanding. And it was tricky. We tried many different things, how to understand the level of understanding in many different ways. But we went back to the question of what we want to achieve from students' interactions. Is it more of factual information recall or more of applying the information they already learned from the experience? So we identify some of the hierarchical structure on our own with the help from the chemistry instructor who had extensive experience in teaching chemistry. So the basic mentioning of the feature is the very basic level of conceptual understanding. To linking, applying ideas is the highest level of understanding. So that's how we identify the level of understanding. Chin-Chung is giving me the signal that our time is up.
Yeah,
okay.
but I also, that's fine, yeah.
Okay, so
Anyways, our time is up, I guess, so it's 4:17. So thank you for inviting me once again. I have to say for myself, this was, I guess, my first real experience of being involved in a real hybrid learning situation where there's people in video, there's actually people, live people in front of me, so it was kind of an interesting experience. Although I would have preferred for you guys really to be here.
We would too.
Hopefully next year.
okay, good.
Yeah.
See you.
Thank you, Joe,
Yeah.
very much.
Thank you.
Yeah, so I think we answer most of the questions. Yeah, and that's we can right now because time's up. We conclude the session here. And if you have further questions, you can just email either one of us. Yeah, and we will try to answer your questions. Thanks for your participation for this session. Thanks, Joe, and thanks everyone.
Yeah, I should also
It's very
mention, just,
early-
I enjoyed
Yeah.
reading the papers, by the way. And you should also know there was a couple of comments that came through that people really enjoyed the imagery, the graphs that you guys showed. So that was a really nice point. A couple of people mentioned that on some of the chat, so thank you.
Okay, good. Thank you so much.
Thank you.
Thank you.